வெல்கம் சார், மோஹித் சர்மா சார்.
சொல்லுங்க.
சார் ஸ்பீக்கர் ஜாயின் பண்ணிட்டார் சார்.
ஓகே ஓகே.
மோஹித் சர்மா சார் ஜாயின் பண்ணிட்டாரு. இஸ் ஜாயினிங். ஆடியோ இஸ் கனெக்டிங்.
Mohit ji, good afternoon. Mohit sir.
Hello, Mohit sir.
I hope so.
Hello.
Hello. Mohit sir.
Hello.
Yeah. Can you hear me?
Yeah.
Hello. Mohit sir, your audio is not clear. Hello. We couldn't hear you.
Let me check it. Oh.
Yeah. Now okay. Now we can hear you.
Oh, okay.
Hello.
Okay, I think now it is.
Hello. Mohit sir. We couldn't hear your audio, Mohit sir. But you are talking, but we couldn't hear you. Sir, better you can quit and then rejoin, sir. I hope so. Some any band.
Yes, sir.
Hello. We couldn't hear you. Mohit sir.
Hello,
Yes, sir. Mohit, sir.
sir. Am I audible, sir?
Yeah, now you are audible.
Okay, thank you. Thank you so much, sir.
It's okay. It's okay. No issue.
Actually, I think some internet problem is there, so
Okay.
that is why
Yeah,
it
now your
is.
audio is very clear.
And let me share my
Ah.
PPT. If it is
Mohit, sir, do you have any bandwidth issue?
sir, is my hello? Yes, sir. Okay, okay, sir. Got it, sir. Uh, Sir, I'm sending you on your WhatsApp. Yes. And I have already shared my profile to WhatsApp. Okay, so no, actually, I'm using a different student laptop, so that is why it is taking time. So okay, okay. Get it, sir. Yes. Okay.
Sir, Subramaniam sir, am I audible, sir?
Yes, ma'am, you are audible. Sir has joined, but he is having some bandwidth issues. Dr. Mohit.
Sir, welcome, sir. Mohit, sir, welcome, sir.
No, he is having some bandwidth issue.
Okay, sir.
So Mohit sir?
Yes, sir.
Yeah.
Yeah,
Is it, is it possible for you to share now?
yes, 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 yes. I'm here.
You just share, sir. No issue. Yes, sir. It is visible. Can you make
Is
it
it-
as a full screen?
Yes, 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 sir.
Yes, sir. Yes, sir.
Now it is visible, sir.
Yeah, yeah. It is visible, sir. Okay, sir.
Okay.
Okay, sir. It is visible now.
I think my
That's enough. No, now again it got the. Kindly make it as a full screen, sir. Yes, sir. Yes, sir. Okay.
is in the slides.
Yes, sir. Yes, sir. It is visible.
Okay, okay, okay.
We will
Then
start
it
at
is
3 o'clock, sir. Shortly.
Definitely, sir. Definitely.
Okay. Okay.
Thank
sir.
you.
Please-
Thank you so much.
Please stay with us. Okay.
Mohit sir, welcome sir.
Welcome, ma'am. How are you?
Yeah, fine sir. How are you sir?
Yeah, I am also fine. Actually, I am just getting troubled by the internet, so that is why I could not talk to you in a brief. So
Okay.
I think that I can talk to you.
Yeah.
I introduce my colleague, Dr. Dhanashekhar.
Hello, Professor.
Hello, sir. How are you?
Yeah, I'm good, sir. I'm good. So how about you, sir?
Yeah, I am also fine. Actually, I was truly waiting for Subramaniam sir call. Actually, he asked me to join for the FDP program. So I said that, sir, whatever you just say, just let me know what I have to do. I'll be always available and make the program successful.
Okay, thank
Okay,
you.
Thank you. Thank you so much, sir.
It's a very good bonding between Subramaniam sir and SRM University, Manirajan sir, and all. So hopefully, and I also searching for the group so that we can form some research activities working on photonic crystal fiber based on sensors, supercontinuum, nonlinear optics, and all kind of phenomena which can lead to the new spectrum generation and all possibilities where the photonic crystal fiber can be used for different types of applications.
Yes, sir. Sir,
Yes.
after the talk, you can give the open call. Then the researchers, many research students are available here. So that if they are interested, then definitely they will join with you, sir.
Yes,
Because,
definitely, sir.
Yeah,
Definitely.
if it is the suitable avenue for them, so if you share your email ID, then they will contact you.
Definitely, sir. I'll be eagerly waiting for that.
Yes, yes, yes. Okay, okay. Thank you. Saravanan sir. Hello.
Naman.
சார்ஸோட போகுதுடா.
A very good afternoon to Dr. Mohit Sharma, sir. And thank you for giving consent, sir. Mohit Sharma, sir, am I audible?
Yes, sir. Thank you so much, sir.
Yes, sir. Yes, sir. We are very much indebted to you. Thank you for being with us, sir. And moreover, today is the last day of our 1 week online FDP, sir. 7th day. After 4 o'clock, okay, we have the small validatory function. Of course, you please, okay, stay on that, okay, line. Please, okay, I mean, complete the validity, okay, function also, sir. Then, okay, we will wind up.
Definitely, sir. I'll be always there.
Yeah. Thank you. Thank you so much, sir.
Dr. Jayalakshmi ma'am.
Sir, shall we start, sir? Sir, shall we start?
Saran sir. Sir, HOD sir.
Yes, sir. Yes, sir. We'll start, ma'am. Yes, ma'am. Please,
Okay,
ma'am.
sir. Okay.
Yes, yes.
Good afternoon to one and all present here. I welcome you all for the 7th day and 7th session of our national level FDP on advanced computational and experimental research in physics. Today's session will be handled by Dr. Mohit Sharma, Assistant Professor, Department of Physics, School of Liberal Arts and Sciences, Modi University of Science and Technology, Sikar, Rajasthan, on the topic photonic crystal fibers for supercontinuum generation. I request Dr. K. Subramaniam, Assistant Professor, Department of Physics, SRM Institute of Science and Technology, to give an introduction about our resource person. Sir?
Yes. Thank you, madam. So, good afternoon, one and all present here. I take immense pleasure in welcoming Dr. Mohit Sharma for this 7th day, 7th session. So, I would like to introduce Dr. Mohit Sharma. Dr. Mohit Sharma has received his BSc and MSc degree in physics in Dr. Bhim Rao Bahadur, Ambedkar University, Agra, India. And he has received the PhD degree from the Department of Physics, Birla Institute of Technology at Lissa, Ranchi. He has published more than 60 research papers in reputed international journals and international conference proceedings. He has involved in several projects with IIT Kharagpur, where he was involved in developing electronic nose and vision for aroma detection. And in another project, he has contributed to developing data acquisition system, that is both software and hardware, for geotechnical instruments. His research interests include nonlinear optics, fiber optics, photonic crystal fiber, supercontinuum generation, soliton generation, optical communication, and fiber optic sensors. He received several national level scholarships such as Sahara India Scholarship in the year of 2003 and Indian Railway Academic Scholarship in the year of 2002, 4, 7, and 9, respectively. He has received the Outstanding Reviewer Award from the Elsevier publication in the year of the 2018 and Outstanding Reviewer Award in the year of the 2016 from the Journal of Optics and appreciation from the several international journals. He has joined several research societies such as IEEE and Plasma Science Society of India as a member and OSA and SPIE as a student member. He also served as a reviewer for many reputed international journals like IEEE, Quantum Electronics, IEEE Sensors, letters, etc. I really welcome you, sir. We have very proud to hear your session. So now the session is on yours. Please take your session.
Thank you so much, sir, for introducing me in front of all dignitaries. And I'm thank you all, HOD sir, Jayalakshmi sir, Subramaniam sir, and all who invited me for this lecture. And I'm really grateful to give a talk on the photonic crystal fiber and about the supercontinuum generation. In this talk, basically, we will discuss about just a second. One thing, co-host ask you start. Okay. So basically, in this talk, we will discuss about some properties and some advantages of photonic crystal fiber and how we can use the photonic crystal fiber for the nonlinear optics and other kind of application. So other kind of application are having a wide range of varieties. So basically, in this talk, I stick on the nonlinear optics, that how the nonlinear optics can be studied by using photonic crystal fiber as a supercontinuum generation. So first of all, before introducing the photonic crystal fiber, I'm just my slide is.
Yeah, slide is not moving, sir. Mohit Sharma, sir.
Yes, sir. Yes, sir. Actually, slide is not moving.
Yes, yes, yes.
Just a second. I'm so sorry.
It's okay. It's okay. Take your time.
Now, is it visible, sir?
Yeah, it is visible. Make it as a full screen, sir.
Yes. Okay. Okay. So before going to introduction of the photonic crystal fiber, first we should know that what is basically the fiber, and before photonic crystal fiber, we have to look onto the conventional optical fiber, which we have already studied in our undergraduate and postgraduate classes. That the conventional optical fiber having a very vast range of applications, such as optical communication, broadband, low attenuation over a long range, and low cost distance communication, fiber optic sensors, fiber optic based devices in biomedical applications, in solid-on lasers, superconducting generation, and optical switching, and different types of couplers. But in that case, there are some limitations of conventional optical fiber, such as it is having a um, uh, single mode at fixed wavelength, because we cannot tailor the particular core and cladding size. So that is why it is fixed for the single mode, and loss is large, not in the sense of other types of devices, but itself for the as comparison with the photonic crystal fiber, the loss is very large. The dispersion is tunability is very limited, because we cannot tune the core and cladding. And for making the nonlinear optical devices, we basically need large peak power to activate those nonlinear phenomena. So in that case, the group of Knight et al. Have introduced the photonic crystal fiber in 1994, and basically the PCF is basically one material device where the cladding is used as a air hole, which run along the core of the fiber. So here we can see the both types of fiber, conventional optical fiber as well the photonic crystal fiber. And what does it mean by photonic crystal and fiber? So we know that the basically these small air hole at the microscopic level, um, they are arranged in a regular pattern, and it satisfies the crystal definition. So that is why it is known as photonic crystal, and it shapes like fiber, so it is called photonic crystal fiber. Sometime it is also known as holy fiber and the microstructured fiber. Basically, there are two types. One is band gap photonic crystal fiber, and another one is index guiding photonic crystal fiber. So in index guiding photonic crystal fiber, if you could see from here, the core is very means the core is solid, and make it with the background material such as the silica and the air hole, which behaves like as cladding. Whereas in the band gap guiding PCFs, the core is basically made by the air holes or the low refractive index material than the cladding. Now, basically, there are two types of PCF, which divided in sub different types, and these types of photonic crystal fiber can be used for different types of application, and can be made for the application requirement. For the now, there are types of highly nonlinear PCF, and what is the mean of highly nonlinear PCF? We can see the air filling fraction is very high in the highly nonlinear PCF. The large mode area, it means that the core size is very big than the conventional one, and highly numerical aperture. Index guiding PCF, in this particular PCF, we basically make anisotropic behavior of the PCF, whereas that can be produced by making elliptical core of the PCF, as well as the random hole PCF. This kind of PCF is sometimes used when some error comes during the fabrication. Same as in the band gap guiding PCFs. Now there are some different types of timeline where we can see that the photonic crystal fiber have been developed for the different types of mean. But after this 2006, it is studied by the different types of applications, such kind of nonlinear optics, sensing applications, biomedical applications, frequency comm application, and different types of application can be used for this particular time. Now, the fabrication process, if we will talk about the fabrication process, there are different types of fabrication process by which we can acquire a good PCF. Now, this particular, if we will talk about the particular fabrication process, there are extrusion fabrication process. In this, basically one tower is there, and we melt the silica glass, and from that tower we put one weight over there, and this particular silica melted, and after melting, this gives a very thin wire or very thin fiber, which we collect from the spooling wheel. Another one is stack and drop technique. In this stack and drop technique, what we basically do the same process as the extrusion fabrication process, but the thing is what we did in stack and drop technique, we make our desired design and put into the funnel, and after that we heated that, and after heating we draw this particular fiber, and after drawing we got the desired design which we wanted to that. Now another one is drilling fabrication process. Drilling fabrication process is a very limited length fiber, for the limited length fiber, in which what we have to do is we have to just drill those designs so that particular air hole will be there, so the cladding part can be designed by the drilling process. Now, if you will talk about the optical properties, now this.
Assume, sir.
Yeah.
What is this tractor system?
Spectrum. I didn't get you. What?
Tractor system. You have used just previous slide.
I could not understood actually.
The lower portion you see this tractor system you have written. What is that tractor system? TRACTOR.
Yeah, where?
Hello?
In the lower portion there is tractor system. In the first line you have written.
Okay.
Hello, sir.
Okay.
Sir, Pankaj sir. Pankaj
Yeah,
sir.
Yeah.
Sir, question session is at the end of the session, sir. So
Okay,
kindly let the speaker to complete the session. So at the end of the session, you can ask the questions and clarifications.
Okay.
Okay? Sir Mohit,
So-
sir, you can continue, sir.
Okay, so I'll just let you know the tractor system is basically to give the direction of particular wire comfortably. Because what happened when it is melted, if you will uh, turn the particular fiber, then definitely it will break down. So this tractor system holds the fiber some types of giving a particular heat so that it can maintain the shape of particular fiber. Okay, so in rest of the thing, I'll just let you in the questioning section.
Thank you, sir.
And now, this photonic crystal fiber is basically having a unique property. And what is that unique property? That unique property is we can tune the optical properties of the fiber, which we cannot do in the conventional optical fiber, such as loss mechanism. Here we can see we have designed some of the fiber, which we can see that the loss is very low, very low. So that means that whatever will the application, the efficiency is increased. So and after that, dispersion mechanism. Basically, for the dispersion mechanism, we generally calculate this dispersion by using Salmir equation. Salmir equation you can see from mouse. Okay, you can see from this second graph, that is n square 1 plus, and this sigma is basically gives the material constant as well as for particular wavelength. Now after this we calculate the n effective and effective refractive index, and after that we calculate the dispersion of the particular fiber. So basically, there are different types of dispersion mechanisms, as we have already studied in undergraduate and postgraduate, like intermodal, material, and waveguide dispersion. So once all the dispersion collected together, they make or they called as chromatic dispersion. So this particular graph is showing the chromatic dispersion. So there are basically three types of dispersion. One is anomalous region, and this is normal region, and the zero dispersion region. Basically, zero dispersion region is very demanding for the activating the nonlinear effect. Now, if you talk about the nonlinearity, so this nonlinearity comes with the optical mode or the effective optical mode area. So that is basically inversely proportional to the effective mode area of the fiber. So here we can see this particular nonlinearity comes around 1000 or between 2000 per watt per kilometer for at communication wavelength. So it is a very high nonlinearity. Now, if you will talk about the Bayer fringes is basically known as the contrast between two different effective refractive index, or we can say the both horizontal mode and the vertical mode refractive indexes. Now, this particular Bayer fringes is basically highly desirable for the sensing applications. Now, this particular trade-off, I have put another relation. What is that? Basically, for studying the nonlinear optics or supercontinuum generation, we need lower dispersion with high nonlinearity. So from this we can see that the C part is having very low dispersion and as well the high effective nonlinearity. And if we will talk about the effective V parameter is basically defined at how many modes it contains. So basically, for conventional optical fiber, for the single mode condition is V is less than 2.4. But in photonic crystal fiber, we are having low loss as well the a very high confinement, and uh, due to that that particular condition raise up to 4.2, and this is not basically a constant value. This depends on the particular photonic crystal fiber which is designed. So it could vary design to design, that how the single mode condition is coming for this. Now this for this particular design which we have calculated, the single mode condition lies less than 4.2, and which can be calculated by using this formula, the effective core area, the square minus effective mode area, effective refractive index of the cladding. Now there are several applications based on PCF, large mode area fibers, delivery of high power optical beam for laser welding, laser amplifiers, and frequency comb. These types of photonic fiber contains very high nonlinearity, which can be used for supercontinuum generation, highly um, and different types of nonlinear phenomena, studying for the Raman effect, studying for the self-phase modulation, and other kind of modulation stabilities. And if we'll talk about the high numerical aperture PCFs, and they are having wide range of applications such as laser endoscopy, optical sensors, and in the biomedical field. Same as we have discussed that the birefringence PCFs used for the polarization sensors or any kind of different types of sensors such as salinity sensors, blood sensors, cell sensor, cancer sensor, and temperature sensors. And this also can be used for the dispersion compensation. Now, if we'll talk about the nonlinear optics and the supercontinuum generation, so basically, first of all, we have to understand that what is basically a supercontinuum generation, or what is basically a supercontinuum. So if we send a particular pulse at particular wavelength, and after having some mix of effects, when they act together on that, it is spreaded throughout the wavelength, and this particular wavelength is called continuum. And when this continuum is having multiple wavelengths, it is known as supercontinuum. So from this figure we can see that there are a picture in a lab. This is not basically by me, this is Barketel in Bath University. So from there we can see there are some PCF, and the light increasing, and once the light increasing, we are getting a spectrum, and that is increasing the light from red to blue. It's mean that it is gaining the spectrum. Now this is having several types of nonlinear effect which act together on it, and I'll just discuss about some of the nonlinear phenomena where which gives rise to the new frequency generation. Now if we will talk about the self-phase modulation, The self-phase modulation is basically is the self-induced phase shift of an optical pulse due to the Kerr effect. When an ultra-short optical pulse propagates into a nonlinear medium, then the refractive index of the medium varies with the intensity due to the optical Kerr nonlinearity. This variation in refractive index produces a phase shift and in the optical pulse, which leads to a change in the pulse frequency, which we can see from here, which we can see from this figure. Ultrashort means through SPM, the ultrashort pulses with high peak power can lead substantial spectral broadening of hundreds of nanometer wavelength. Typically, a strong oscillation appears when SPM effect is dominant and the much weaker dispersion effect. So this gives the basically the rise of new frequency generation, and we can see that this particular phenomena gives multiple pulses which act together and gives a very wide range of spectrum. Now, if we will talk about the modulation instability, another kind of nonlinear phenomena, the modulation instability is the nonlinear amplification of fluctuations on propagating optical pulse. So this modulation stability generated sideband frequency and breaks up the optical beam into a series of ultra short optical pulse. So MI mainly occur when an optical pulse is pumped in anomalous dispersion region. Perturbation causes the increment in the pulse intensity at particular point. This pulse undergoes SPM effect, means the self-phase modulation, and then the compress due to the anomalous dispersion. And this process of peak intensity increment continues with the power increase. This we can also show from here. Once the power is increasing, the modulation instability is increasing. So in this process, the MI is dominant over the other processes and produces two spectral sidebands centered at the frequency, appears at the fiber end. Now, there another kind of nonlinear optical phenomena is self-steepening. What is basically a self-steepening? It plays a vital role in spectral broadening for ultra-short dispersion. The occurrence of self-steepening is due to the intensity-dependent group velocity. At peak of the optical pulse has higher group velocities than rest of the co-property. The pulse propagates with lower velocity in the comparison to the rest of the pulse. As the result, intensity gradient. The intensity gradient of the leading edge is reduced with the trailing edge increment. And due to the self-steepening effect, the spectral broadening of the pulse through SPM occur asymmetrically with blue shifted spectral broadening and higher red shifted spectral intensity of the spectrum is conserved energy in the FWM process, means the four-way mix. Now, for four-way mixing process, basically, we can see the temporal picture of that particular four-way mixing. And what is basically a four-way mixing? This is basically a non-degenerated process for four optical wave interaction non-linearly inside a dielectric medium or the fiber. When two optical pulses or wave with different frequency passes through a dielectric medium, then due to the refractive index modulation, it generates two new frequencies. So the optical pulse wave, the new frequency originated only when the phase matching condition is satisfied. And what is that phase matching condition? So both the frequency which is inserted and both the frequency which is newly generated. If you will check the particular sum of that, there will be some particular phase matching condition. And that should be near to zero as possible. So degenerated four-way mixing occurs when basically the two input frequencies nearby equal to each other. When two pumped optical waves are combined together to generate signals and the ideal, these two new frequency optical waves generated from the noise and their position depend on the cross phase matching condition. The four-way mixing mechanism underlies many nonlinear effects, including SPM, X means this cross phase modulation, and MI, etc. Now, if we will talk about the XPM, means cross phase modulation, it occurs basically when two or more optical beams launch simultaneously into a nonlinear medium. From physical perception, the cross phase modulation is generated due to the changes in the effective refractive index, which affected by the optical beam intensity as well as the intensity of other co-propagating optical beam. The new frequency are efficiently generated when the phase matching condition is satisfied. The XPM induced phase shift depend not only the shape, and the width of the pump, but also fiber group velocity mismatch, which comes from the four-way. When pumped and signal beams are pulsed, then the phase shift is also depend on the relative time delay between the pump and signal pulses. And this particular phase shift can be controlled by the initial time delay. So it generally occur, but for checking the cross phase modulation is very tough in the sense of observing from fiber to generating a new frequency, but it always consider that the XPM or the means this cross phase modulation plays its vital role in the new frequency generation. Now, if we'll talk about the Raman scattering. So this Raman scattering is different from the Raman because in that particular Raman effect, we know that some molecule vibration is there, and there are basically three frequency we achieve. One is the same frequency of incident light, which is called Rayleigh scattering, and the addition of frequency, which is Stokes line, and the subtraction of the frequency is basically known as the anti-Stokes lines. But here in estimated Raman scattering, this is basically an elastic process of energy transfer of the photon due to the rotational motion or the molecular vibration motion. When high intensity molecular optical beam propagates inside the optical fiber, the Raman scattering occur and shift some of the photons due to new frequency, which we can see from this particular graph. This particular graph, I'll just explain in the next slide. So from here, we can easily see that this particular red color shows the high intensity and the blue color shows a low intensity. So from the picture, we can see that the intensity is shifting from means shifting to red shift and giving a particular soliton. Soliton means it is maintaining the height and the means the amplitude and the motion throughout its propagation length. So when this high intensity monochromatic optical beam propagates inside the optical fiber, the Raman scattering occurs and shift of some photon to new frequency. These scattered photon either gain energy, which is basically known as the anti-Stokes shift, or the lose energy, which is known as the Stokes shift. The optical pulse experiences as energy amplification toward a lower frequency, which causes a red shift of the optical pulse. This red shift process of the optical pulse is also known as the soliton self-frequency shift. In silica glass, this effect contributes to the enhancing the broad range of frequency shift due to the amorphous nature of the material. Means the molecular vibration frequency in the physics term, we can say the molecular vibration frequency form a wideband superconducting generation. So these are some basic nonlinear phenomena which I have discussed here, and each of nonlinear phenomena having wide range of research. So I covered all of them, and that can be studied particularly for any kind of application. Now, this is particularly supercontinuum. Now, there are some key points of supercontinuum generation. The efficient generation of supercontinuum is desirable in any medium. For the generation of supercontinuum, there is some following at least conditions which must be fulfilled by the PCF or any other nonlinear medium. And what are those? Basically, it generally required an ultra short pulses for supercontinuum generation. And PCF length must be shorter than the soliton or the soliton piezo. The effective mode area should be as small as much we can, because in earlier slide we can see that the nonlinearity is inversely proportional to the effective mode area. So if we want to get the high nonlinearity or ultra high, then it means that we have to design is such kind of fiber which gives a very low effective mode area. And another requirement is for ultra means for wide range of supercontinuum is it must have lies near to zero dispersion. So in order to increase the nonlinearity of medium, PCF4 may consist of material with high nonlinear refractive index. So there are some optical parameter requiring to give a wide range of continuum. Basically, this trade-off basically I have made for choosing the particular photonic crystal fiber parameter to study further. So for comparison, I have drawn some different types of fiber which are having different types of parameters. This lambda shows the air hole pitch, which gives the distance between two simultaneously air holes. So from here we can see that the particular different types of sample which I have given name A, B, C, and D. So A is here, B is here, C, D, and E, and we can see that A is having very large effective nonlinearity as well the dispersion, and B is having large nonlinearity but dispersion in normal region, and F is having very low nonlinearity but high in dispersion. So in the case of getting wide range of supercontinuum, we always require the fiber with the parameter having a dispersion at near to zero as well high nonlinearity. So in that case, we are having this C type of PCF fulfilling all the condition to get supercontinuum generation. So from this we can calculate that which parameter will be helpful to generate a supercontinuum generation. Now, why we are studying all kind of supercontinuum and how we can tune? So this is basically a normal parameter graph that for picosecond and larger pulses, if this pulse propagates in the normal ZBD region, then we generally get four-way mixing, Raman scattering, and self-phase modulation. Or the continuum is responsible by this nonlinear phenomenon. And if it is having picosecond and larger pulses with anomalous GBD region, then we generally get modulation instability, Raman induced self frequency shift, and dispersive wave generation. And what is this? Basically a dispersive wave generation. Actually, this dispersive wave generation having no particular definition. So it means if chunk of radiations coming out having no explanation, generally we described as the dispersive wave generation. So I'll just let you know about this dispersive wave generation. So if we give higher pulses like sub-picosecond pulses propagate in a normal ZBD region, basically we get self-phase modulation, phase wave mixing, and Raman scattering. And in anomalous GBD region, we basically get the supercontinuum by soliton fission, Raman scattering, and dispersive diffraction. Now, here we can see the density graph representation. So this density graph representation can be seen here as the red light shows the high intensity and the blue light shows very low intensity. And we can see from this particular picture that the energy is transferring toward the higher wavelength. And this maintaining it's throughout the amplitude, which is defined as the soliton. As well, these dispersive wave generation we generally get in the background. This particular point where the all nonlinear phenomena start activating is generally that point is known as the soliton fission. So now for the theoretical background, basically we are having nonlinear Schrodinger equation through which we can calculate the supercontinuum, where this term, this term is basically a pulse parameter. This term is the first term is known as the loss term. This beta term is basically a dispersion term, and this is nonlinear term, and this is Raman term. So the Raman response function can be calculated by using Kramer-Kronig relation. And these Kramer-Kronig relation basically require an imaginary refractive index of that particular material. So for SF57, it is generally a coefficient of tau1 and tau2 of 5.5 fs and 32 femtosecond. Now, basically, there are two types of parameter we require for the generation of supercontinuum. First is fiber parameter, and another one is optical parameter. Oh, sorry, pulse parameter. So for pulse parameter, what we require and what we need is that what pulse shape we are propagating, what is the pulse width, at which wavelength we are propagating that particular pulse. And after this, beyond this, basically we require a medium parameter. It means the fiber parameter. Air hole pitch, it generally basically not required because we require dispersion coefficient and fiber length. So dispersion coefficient basically the chromatic dispersion and the up to 10th order of dispersion we calculated. And why we generally require these types of dispersion, this higher order dispersion basically help to tune the supercontinuum, and fiber fiber length is also play a vital role for shorter wave, for shorter fiber length. We generally get a very good supercontinuum, and the nonlinearity, which is also a fiber parameter, and Raman response. So basically, this is the basically all about the supercontinuum and the photonic crystal fiber. It is having a wide range of application, and each of the topic which I have discussed having different types of branches in it for working toward the different kind of application. So each of the nonlinear optical phenomena having different kind of studies. So basically, I thought that this particular PPT will give a brief information about the photonic crystal fiber and the supercontinuum generation, that how the supercontinuum activate and how the nonlinear phenomena takes place to give rise the bandwidth of the continuum. So for this, I'm now ending my PPT, and now I am open to all your queries. If you are having, then
Okay.
I'll.
Okay. Thank you very much, Dr. Mohit Sharma sir, for giving a wonderful lecture on the photonic crystal fiber on supercontinuum generation. So
Thank you,
really, you have given a talk from the basic principle onwards. So it's really wonderful. So I hope so. Those who are entering the research field, okay, so it's very useful for them to trigger them to turn their research into your avenue. So it is I'm really thankful to you. So now I call any queries from the audience side. You can ask any questions if you want. You can ask.
Dear participants, please mute yourself, please.
Very nice talk, Dr. Mohit Sharma sir. Wonderful talk about photonic crystal fibers and its application. Thank you so much. Thank you so much.
Thank you so much, sir,
Yes,
for
yes.
giving me this opportunity to spread this knowledge to every researchers, and I hope that everyone will be interested to work with this.
Yes, we have received overwhelming responses from the participants across India. Thank you so much.
Participants, you can ask questions related to this topic. So if there is no question, is there any question here? HOD sir, shall we move into the valedictory part?
Yes, sir, we will. If
Okay,
there are no more questions from the participants, we will move on to valedictory session,
Okay,
sir. Yes.
So really wonderful session, and then so all the 7 sessions are completed. Today is the last day of the FDP. So thank you, audience. Thank you, participants, for your continuous support. So every day there is not less than 200. So 200 plus participants. So really we are appreciating you for your active participation in the session. So now I invite Dr. V. Jayalakshmi ma'am to give the overall feedback of this FDP.
Thank you, sir. Good evening to one and all present here. I'm very fortunate to give the overview of our national level faculty development program on advanced computational and experimental research in this year 2022. So we got an overwhelming response each and every day, which is not less than 250 on every day in Zoom and YouTube. Thank you all participants. On the first day, 20th June, our FDP starts with a keynote address by Dr. B. Venkatraman, Director, Indira Gandhi Center for Atomic Research, Kalpakkam. He encouraged researchers to speculate in their field. Followed by keynote address, the first session was handled by Dr. M.S. Manirajan, Assistant Professor, Department of Physics, University College of Engineering, Anna University, Ramanathapuram. He delivered his lecture on role of computation in nonlinear dynamics. He has elaborated on various analytical methods to solve nonlinear partial differential equations. On the next day, 21st June, the second day and the second session was handled by Dr. Muthu Sendil Pandian, Research Scientist, Photovoltaic Device Laboratory, SSN Research Center, SSN Institution, Kalavakkam, has delivered his lecture in development of high-quality, non-linear optical single crystals for second harmonic generation device application. He elaborated on crystal growth by SR method and modified SR method. He explained about how to harvest the crystal. He also explained physical properties of the crystal. On 22nd June, the third session was handled by Dr. K.J. Sankaran, Senior Scientist, CSIR, Institute of Minerals and Materials Technology, Bhubaneswar, Odisha. He has given lecture in microplasma materials, devices and applications. He explained about plasma and microplasma. He elaborately explained about generation method, device fabrication, characteristics and applications of microplasma. On 23rd June, the fourth session was handled by Dr. Dattatreya Latte, Professor and Head, Center for Nanoscience and Nanotechnology, Amity University, Mumbai, Maharashtra. He gave his lecture on 2D nanomaterials for technological applications. He explained about 2D materials-based flexible and wearable sensors for various medical applications like prevention, the cardiovascular diseases, and measuring the body temperature, pressure, and emotional detection. On 24th June, the fifth session was handled by Dr. E. Meher Abhinav, Assistant Professor, Department of Electronics and Communication Engineering, K.G. Reddy College of Engineering and Technology, Hyderabad. He gave talk on environmental friendly refrigerant magnetocaloric materials. He explained about in-depth studies of magnetocaloric materials and its applications. On the next day, 25th June, the sixth session was handled by Dr. S. Arun Mehta, Associate Professor, Department of Electronics and Communication Engineering, KLEF University, Andhra Pradesh. He gave his lecture on energy harvesting technology for IoT. He briefly explained about how Internet of Things are working and generating the power from different ways of sources. Today, the last session has been handled by Dr. Mohit Sharma, Assistant Professor, Department of Physics, School of Liberal Arts and Science, Modi University of Science and Technology, Sikar, Rajasthan. He has given his talk on photonic crystal fibers for supercontinuum generation. He explained about photonic crystal fibers, classification of photonic crystal fibers, fabrication process, optical property and application. He also explained about nonlinear optics, supercontinuum, and he also explained about mechanism of supercontinuum generation. Participants, I thank you one and all present here, and you gave a overwhelming response to us for all the 7 days. Thank you one and all.
Thank you, ma'am. Thank you for your wonderful presentation. And then I invite Dr. M. Saravanan, HOD Physics, SRM IST Ramapuram campus, to deliver the valedictory. Sir?
Yes, sir. I'm audible, sir.
Yes, sir. Yes, sir.
Yes, sir. Today's resource person, Dr. Mohit Sharma, sir, from Modi Institute of Science and Technology, and our beloved participants, a very good evening to all present here. We, the Department of Physics, SRM Institute of Science and Technology, Ramapuram campus, successfully organized 2 weeks FDP on advanced computational and experimental research in physics for the past 2 years. And due with the overwhelming response, we are motivated to organize such type of FDPs in series. Okay, we have proposed to conduct these 1 week FDP on advanced computation and experimental research in physics during the 20 June to 27 June 2022. In these FDP, we have invited Dr. P. Venkatraman sir, Director IJK Kalpakam, and who has graced this occasion as a chief guest and delivered the keynote address during the inaugural function of the first day. We have identified the most eminent resource persons from various well-recognized and research institutes in India, such as Modi University of Science and Technology, Rajasthan, Amity University, Mumbai, SSN institutions, Chennai, CSIR, Institute of Minerals and Materials Technology, Bhubaneswar, KL University, Andhra Pradesh, KG Reddy College of Engineering Technology, Moinabad, Hyderabad, Telangana, and Anna University, Ramanathapuram, Tamil Nadu, but delivered the lecture on the recent development in computational and experimental physics for the applications of science and technology. Further, we have received the overwhelming response from the participants across India. Every day, more than 270 participants were participating in this FDP and acquired the knowledge in the future development of science and technology. On behalf of Department of Physics and SRM Ramapur campus, I thank our chief guests and all our resource persons and participants who made these 1 week online FDP a grand success. Thank you.
Sir, it is a usual custom that we give an open invite to the participant to give their feedback. So now I call upon the participants. You can unmute yourself and you can give your feedback on this 1 week FTP, so that anyone you can unmute yourself and then you can give your feedback.
The participants are giving feedback in the chat box.
If anyone is willing to give the feedback, you can unmute yourself and then you can give.
The participants are giving feedback in that chat box only, sir. Okay.
Okay. Okay. So now I call Dr. M. Dhanasekaran sir to deliver the vote of thanks.
Thank you, sir. Good evening, one and all. I take this opportunity to thank our Honorable Chairman, SRM Institute of Science and Technology, Ramapuram campus, for his constant support to organize this 1 week national level faculty development program on advanced research in physics. On behalf of the management and the Department of Physics from SRM IST Ramapuram campus, hardly thanks to our chief guest, Dr. B. Venkatraman, from director from IGK Kalpakam, who gave a keynote address for the first session of this FDP. And my sincere thanks to all the resource persons who have delivered a wonderful presentation for this 1 week FDP. Finally, my heartfelt thanks to our Chief Director Sir, Dean ENT Sir, VP Academic Sir, VP Admin Sir from SRM IST Ramapuram campus for their constant support and motivation to make this one week national level FTP a successful one. Last but not least, I thank all the participants and my colleagues who have actively participated in this 1 week FDP. Thank you very much.
Thank you, Dr. Mohit sir.
Thank you so much for being with us, sir. Thank you so much for your wonderful talk on this last day session. So,
it's my pleasure, sir.
Yes, sir. Yes, sir.
Thank you so much, sir.
We'll keep on touch with you, sir, for our forthcoming events.
Okay. Participants, you can note Dr. Mohit Sharma's email ID that is visible in the screen. If anyone is interested in the nonlinear fiber optics, you can you can contact him. Mohit ji, now you can leave ji. Thank you.
Okay, thank you so much, sir.
Thank you.
Yeah, thank you so much, sir. Mohit Sharma, thank you so much for being with us, sir. Thank you.
Thank you, sir.
Thank you, ma'am. Have a nice day.
Thank you.
Thank you, Mohit sir.
Dear audience, dear participants, we will give the certificates only after a week. So kindly don't send the frequent mails and calls. So because we need to process and then we will give the certificate minimum 1 week. After the 1 week, we will give.
Sir, shall we close, sir?
Yes, madam. If all the participants have filled the feedback, okay, we can wind up and close. Once again, thank you all the participants. Thank you all.
Thank you, participants. Thank you, one and all. Subramaniam, sir.
Subramaniam, sir. Okay, sir.
Yes, sir. Yes, sir. Shall we close the meeting, sir?
Yes, sir. Yes, sir. Yes, sir.
Okay, sir. Thank you. Thank you, sir. Okay.